Have you ever wondered why generating text with large language models feels so sluggish? A 70 billion parameter model seems to crawl, outputting just a few words per second. You might think the GPU is working at full capacity, burning through complex mathematical equations. But the truth is, the GPU is actually idling. It is trapped behind a physical barrier known as the memory bandwidth bottleneck. Today, we will explore speculative decoding, the brilliant, mathematically rigorous algorithm that breaks this bottleneck to speed up LLM inference by 2 to 3 times, with absolutely zero loss in quality. To understand why LLMs are slow, we have to look at arithmetic intensity. In standard autoregressive generation, a model produces text token by token. To generate a single token, the GPU must load every single parameter of the model from high bandwidth memory, or HBM, into the fast on-chip SRAM cache. For a 70 billion parameter model, that means transferring 140 gigabytes of data across the memory bus just to calculate a single word. Because memory transfer is orders of magnitude slower than arithmetic computation, the GPU cores spend over 90% of their time sitting idle, waiting for data. Standard generation is completely memory bandwidth bound. How do we solve a physical hardware bottleneck with a clever software algorithm? The answer is speculative decoding. Imagine you need to write a highly technical report. Instead of having a senior researcher draft it word by word, you hire a fast junior writer to draft several paragraphs. The senior researcher then reviews the draft in a single, swift sweep, correcting any mistakes, but accepting everything that looks correct. In the AI world, we use a tiny, fast draft model to speculate several candidate tokens and a large, slow target model to verify them all in parallel. Here is how the collaboration works in detail. First, we run the small draft model autoregressively for k-steps. Because the draft model has far fewer parameters, it can load its weights and generate candidate tokens extremely quickly. For example, if k equals 4, the draft model rapidly generates 4 candidate tokens, one after another. These tokens are cheap to produce, but they're just educated guesses. They might contain grammatical errors or misinterpret the prompt, so they cannot be trusted blindly. Next comes the masterstroke. We feed the prompt and all 4 draft tokens into the large target model simultaneously. Normally, running the target model 4 times would take 4 slow memory load cycles. But because the draft tokens are already written, we can process them in a single parallel forward pass. The target model computes the exact probability distributions for all 4 positions at once. We have traded serial memory accesses for a single parallel computation, fully utilizing the GPU's idle compute cores. Now, how does the target model decide which draft tokens to accept? We cannot just accept tokens where the target model agrees, because that would alter the final probability distribution and degrade model quality. Instead, we use a stochastic acceptance algorithm. For each draft token, we compare the target model's probability, P, to the draft model's probability, Q. If the target model's probability is greater than or equal to the draft model's, we accept the token. If it is lower, we accept it stochastically based on their ratio, keeping the final output mathematically identical to the target model alone. What happens when a draft token is rejected? Suppose the first 2 tokens are accepted, but the third is rejected. We immediately discard the 3rd and 4th tokens. But we do not go home empty-handed. In the same parallel forward pass where the target model verified the draft, it also calculated the true probability distribution for the next token at the rejection point. We sample from this corrected distribution to get a brand new, verified token on the spot. In this single step, we successfully generated 3 verified tokens while only loading the large model's weights once. Behind the scenes, we also have to manage the model's memory state, the key value, or KV cache. The The KV cache stores past key and value vectors to prevent redundant calculations in future steps. When the draft model speculates tokens, both the draft and target models update their KV caches. But when a rejection occurs, those speculative cache entries become invalid. The algorithm must dynamically roll back the KV caches of both models, printing the entries corresponding to the discarded tokens so that the next round of speculation starts with a perfectly clean history. The performance impact of speculative decoding is staggering. In practice, draft models achieve high acceptance rates, often accepting 3 to 4 tokens per draft cycle. This translates to a direct 2 to 3 times speedup in wall clock latency. And because the stochastic verification math is exact, the output is guaranteed to be identical to what the large target model would have produced on its own. It is a pure win: faster response times, lower hardware costs, and absolutely zero compromise on quality. Speculative decoding teaches us a profound lesson about modern artificial intelligence. We do not always need faster transistors or bigger chips to build faster systems. By understanding the physical layout of our hardware and designing algorithms that align with its strengths, we can unlock massive performance gains. If you enjoyed this deep dive into the engineering of speed, subscribe to Gemini 3.5 Flash Model for more insights. Remember, true optimization isn't just about raw horsepower. It's about working smarter.